And it's funny, all I've been hearing about is the weather. Hot, hot, hot. So I dress short sleeves and it's not hot, hot, hot today. I listen to the weather every day. I really have an interest. I listened to, what's his name? Finan, Mark Finan on YouTube. I've been listening to him for years, even when he was on TV. And I, I was taking an economics class at AR when I was going to school there back in the 60s. And Tom Duhane was a weather guy, and he was in my class. And what's interesting about TV personalities is when you see them in person and hear them talk, they sound totally different than on TV. I mean, totally different. I was just flabbergasted at how different. And he wasn't arrogant or stuck up or anything. He was a really nice guy. But anyway, he went on to bigger and better things. But I've always been interested in the weather. So, okay. Solution. All of you heard the term solution. Most people don't understand the full implication, though, of what the term solution means, though. Solution is more than just liquids. Most people think of like a sugar solution or a salt solution. A solution is two or more chemicals in a homogeneous environment, not heterogeneous. Homo means you cannot tell them apart. Vodka. What's vodka? What's it made out of?
Potatoes.
Huh? It's made from potatoes, yeah. But what do you get from the potatoes? Is yeah, and the technical, there's a lot of alcohol. One is ethanol, 2-carbon alcohol. But it's not pure alcohol, is it? What else is in there? What does the proof mean? 50 proof. That has to do with percent alcohol. Okay. So vodka is usually half and half water and alcohol. Can you tell the difference between the water and the alcohol? Nope, not a bit. Hence, it's a solution. What about when you have your coffee and you have it well filtered? No crud in it. Can you tell the caffeine from the water? No, so it's a solution. Can you tell the sugar from, no. So those are also examples of solution, okay? However, it's not limited to liquids. In this room, there's a whole bunch of gases. Nitrogen, oxygen, carbon dioxide, hopefully not too much carbon monoxide. Can we tell the difference? Can we see, oh, the oxygen's over there, the nitrogen's over here? No, it's all homogeneous. That's a solution. Ring. Okay. My wife has passed, so I'm not wearing a wedding ring anymore, but when you look at the ring, it looks yellow, right? It's not pure gold. It's got some copper in it to make it stronger. Can you see the difference between the copper and the gold? It's also a solution. But most people think of solution as liquids. And that's what we're going to focus on in Unit 3, are the liquid versions of the solutions. Okay. Now, in all solutions, there are two parts. One part is called the solvent, and there's only one of them. And that's the most. And then the other part are called the solute. And you can have one or more. For example, in the air here, we have what's the solvent in the air? Nitrogen, because it's mostly nitrogen. Okay, so the solutes would be oxygen, carbon dioxide, water vapor, those kind of things. Okay, but all solutions have those two parts. One solvent, which is the most, and then solutes, and there could be more than one. Now, Let me see here. Okay, if we were going to take an ionic solid like sodium chloride, salt, and we threw it in water, what happened? Yeah, it dissolves, right? And as long as we don't put, 2 pounds in a little bitty cup, you put a little bit of salt in there, it dissolves. It becomes invisible, so it forms a solution, right? A homogeneous solution. Now, salt, I'm not going to walk over there. Salt tends to be very polar. Water is equally as polar. So when you put polar solids like sugar, specifically table sugar or glucose or fructose, sugars in water, sugars are polar, water is polar, so they dissolve. And there's a term that you've probably heard before, like dissolves like. So if the thing is polar and you put it in a polar solvent, it's going to dissolve. Sometimes slowly, sometimes really quickly. Depends how soluble it is. I'm going to talk about why sometimes it's quick and sometimes it's slow. Okay? Non-polar stuff and non-polar, like dissolves like. If you have some grease on a pan that you're trying to wash and you pour water on it, what happens? Nothing. How do you clean it? Soap. Soap is a unique compound. It's called a surfactant, and surfactants have a polar and a non-polar part. So what happens is the surfactants or soap sticks to the grease, which is non-polar, and sticks to the water, which is polar. And away they go down the drain. Like dissolves like. So if you didn't have soap, you could use something like a solvent, like pentane or MEK or some kind of a paint thinner. And that would dissolve the non-polar grease, like dissolves like. Now, if you don't want to use solvent in your sink, like pentane or gasoline, you use soap, and then you can use water. Think of soap as glue. That glues the polar to a non-polar. So all soaps have to have 2 parts. In fact, in my organic class, we just made soap last week. We got to take it home. In fact, they made ivory soap. They made lye soap. Okay. So this is how polar stuff dissolves. What happens is the polar solvent has got parts that are more positive than other parts. So it's kind of divided between positive and negative parts. It's not totally negative or totally positive. What we do is we label it like this, with this little squiggly mark. This means partially negative. Now, for those of you who are going to take a lot of calculus, when you get into differential equations, you're going to find this is a partial, instead of a big D, that it's a partial D. And this will make sense for those of you who have calculus. Okay? Anyway, we use it generically to mean partial. So this is partially negative, not full negative. Sodium chloride is not partial, it's full positive, full negative. It's still polar though. So what happens is the positive parts of water attract the negative parts of the salt. The negative parts of the water attract the positive parts of the salt. So this is an interaction here. Now, something we haven't talked much about is temperature. When I tell you there's temperature, what does that mean? Yeah. Perfect. Temperature is the metric we use to determine how much kinetic energy the molecules have. Kinetic energy is the energy of motion. Higher the temperature, the more the molecule's moving. When we cool the temperature, it stops moving at minus 273 degrees Celsius. Minus 273. That's the absolute temperature scale. So unless we're at absolute zero, stuff is moving around. What happens is the water bumps up against the salt. So which dissolves faster? Cold tea or hot tea when you're putting sugar in? Hot tea, that means the molecules are moving faster. So they hit the sugar faster. So the chance of the attraction going on is improved with improved interaction. It's improved with increased heat. That's why heat will dissolve things faster, because they're moving faster. So the odds are it'll hit the salt crystal more often, okay? More often. Okay, so one way here, can you tell I've used this before? Oh yeah, right here. Okay, there are three ways that the dissolution of a solute is affected. Okay, I already mentioned temperature. So temperature is directly related to the speed of dissolving. Higher temperature, faster speed of dissolving. Okay, if we stir our coffee with sugar in it, it dissolves faster because we're increasing the chances of the sugar and water coming into contact. So physical agitation is also proportional to the speed of dissolving. Stir it faster, it dissolves faster. And the last one's kind of weird. Which dissolves faster, a cube of sugar or powdered sugar? Why? You're right, but why? It's the surface area. Now, this dissolving bit is a surface area phenomenon. The more surface area, the chances of the water hitting that solute is greater. So if we increase the surface area, we increase the chances of that solvent hitting the solid sugar or salt or whatever. That's why powdered sugar dissolves faster than granulated sugar. If you put rock candy in there, that is one crystal of sugar, big giant one. It takes forever to dissolve because the surface area is small compared to other kinds of sugar. So confection sugar, which is also called powdered sugar, used a lot in baking when they want it to dissolve really fast. They want the consistency to be smooth, like a cake frosting. So they use the different properties of solutes to their advantage. Okay, so these are the three ways that will affect. And again, this symbol here is directly related. Something that's indirectly related is 1 over that symbol. That means when one goes up, the other goes down. One goes down, the other goes up. That's indirectly related. So with solutions, it's all directly related. We're going to find when we get to gases, some gas stuff is inversely related. Like, for example, pressure and volume. Those are inversely related. Okay. And again, temperature is a metric for how much kinetic energy the solvent molecules have. Now we're going to find there are two temperature scales, Celsius and Kelvin with a K. Kelvin is absolute temperature. Celsius is just arbitrary. When water freezes, it's 0. When it boils, it's 100. Totally arbitrary. Just like Fahrenheit, 32 and 212. Arbitrary. some king somewhere said, "Thou be it," and it was like the 12 inches for their foot. Okay. Now let's look at two situations here. Let's take two polar solutes, sand and water, or sand and salt, in a polar solvent, water. When we put table salt in water, sodium chloride, it dissolves. We put sand in water, it doesn't dissolve. They're both polar. Silicon dioxide is sand, also glass. Notice when it rains, the glass doesn't dissolve. Or if I have a glass, that's plastic. If I have a glass of water, it doesn't just blah. Why? There are two forces acting in this water environment. One is called solvating force. Solvating force is what pulls the crystal apart. The other force is crystal lattice force. The crystal lattice force is what keeps it together. So we have a battle of the century. Which force is greater? If the solvating force is greater, it dissolves. If the crystal lattice force is greater, it doesn't dissolve. So with sand, we have a crystal lattice force that's very strong. In fact, it takes thousands of degrees for glass to melt. That's because it's really, crystal lattice force is very, very strong. Where with salt, it's very weak. So those forces are always competing with one another. All solutions have that going on, particularly liquid solutions. Now, so if the solvating force is greater than the crystal lattice force, it dissolves. If the solvent force is less than the crystal lattice force, it stays intact. Does that make sense? Okay. However, the crystal lattice force is not affected by temperature very much. Solvating force is very temperature sensitive. So if we put salt in water and it doesn't dissolve, what do? We up the solvating force by increasing the temperature. That's why it dissolves. So solvating force is directly related to temperature. Crystal lattice force is not, but it's a little bit. You know, like we can melt glass and we get up to 1,500, 1,800 degrees. So it takes a lot of temperature to overcome sometimes crystal lattice force. But in general, it's not affected. Like in our everyday life, not affected at all. Okay, on your next test 3, I'm going to ask you this question. Explain how a crystal of salt dissolves. Okay. And you just kind of take a little diagram, a little explanation. And this is the qualitative part of Unit 3. Okay. Let's look at some common solutes like sugar. This is what glucose looks like. What do you notice right away about that sugar molecule? It's got lots of what? Hydrogen, what else? Oxygen. And this is a line drawing, so there's carbon in there as well that are at the intersection points of the lines. Whenever the line has a kink, there's a carbon there. It's just a shorthand way of writing complex molecules. If you take Chem 2B, you're going to know how to draw these big time. And this happens to be alpha form of glucose. There's D, L, alpha, beta forms of glucose. And there are 16 of them, hexoses. So it gets kind of wild with all the structures. That's the hard part of organic, at least for 2B, is the you've got complicated structures and you've also got synthesis going on. Like I might say, how do you make that? And what are the conditions? You got to come up with, well, you take this and mix it with that. That's the other part that's tricky in organic. Okay, so why do you think this dissolves easily in water? Here's water again. Oops. Yeah, remember, like dissolves like. Water's got OHs in it. What does sugar have? Lots of OHs. Now, that's drinking alcohol, ethanol. One of the big things that are going on in the carb world is another name for carbohydrates are polyols. Poly means many. OL, it has to do with alcohol, polyols. They're used as artificial sweeteners a lot. Glucose is sweet. Fructose is sweet. Sucrose, sweet. Mannose, maltose, lactose, all those are sweet. Okay, and ethanol is not necessarily sweet. What does ethanol do that sugar does not do? You eat sugar and drive all the time, right? And then obviously you can't do the other and drive. Why? What does ethanol, that 2-carbon alcohol, do that sugar does not? It makes you intoxicated, right? That's because it passes the blood-brain barrier. Sugar doesn't. What does the 2-carbon alcohol there, ethanol, do to your liver? Drink too much of it. It's called cirrhosis, right? Guess what sugar does if you eat too much of it? It does the same thing to your organ. That's why a lot of people think that carbohydrates and alcohols, since a carbohydrate kind of looks like an alcohol, that OH does the same sort of stuff to your body. If you drink that alcohol, that's called methanol. Ethanol is a 1-carbon alcohol. In World War II, sailors, submariners particularly, found out you can drink that stuff and it makes you drunk. Because in torpedoes, the inertial guidance system of of a torpedo, they used to take the gyroscope and float it in methanol. And the sailors found out, so they would take the torpedoes apart and drink that stuff. Guess what that stuff did to you? Makes you blind. It's very poisonous. Does the same thing as the other one, though. It's just not as bad for you. So all this food-related stuff is very organically and chemistry oriented and interconnected. It's very interesting. And there's other alcohols out there also that have the same deleterious effects. You don't need sugar in your diet. You know why? Your body requires it. Your body needs glucose to your brain. What happens when you don't have enough? Your body makes it. It's called gluconeogenesis. You got a problem with not enough sugar? Body says, not a problem. I'm going to make it from fat. If you don't have any fat available, you make it from muscle. The brain is the last to go. The brain will make your body make glucose. There's a whole section I have on glucose metabolism and catabolism. It is very complex, but it's very interesting the way it works. It's highly regulated and all this stuff. But it's interesting. A lot of diabetic clinics put their patients on a no carb diet, 0 carbs, and they do fine because your body makes it and they can eat whatever else they want. You want fatty meat, protein in it, fat, have at it. They do fine. And their blood sugar also down. High blood sugar is very bad for you. I sound like a doctor now. Very bad for you. It does bad things to your body. So you want to maintain your blood sugar at a certain level. Like fasting level, for example, should be between 85 and 110. Closer to 85, the better. Anyway, so this whole thing on solutions, that's why sugar dissolves so easily in water. All these OH groups makes it very polar, hence like dissolves like, it dissolves easily. Sorry about the soapbox on sugar. I get into these conversations all the time. Oh, you teach biochemistry. What about blah, 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 blah. So we get into this all the time. Okay. Okay, so that's the qualitative part of solutions. I want you to feel comfortable. What is a solution? How can we change its solubility? And solubility is measured in grams per milliliter. And it's very similar to density. And you'll get a solubility table. And when we get into something called double replacement reactions, we're going to be revisiting this solubility again. I'm going to give you a solubility table. In fact, it looks like this. And what I've done is I've done a graphic version of it. And when you get into 1A and 2A, 3A, they're going to make you memorize the rules. But I did it totally graphically. So all you need to say is these two things together, if it's white, it doesn't form a solid. If it's black, it forms a solid. Like, really easy to use. Unlike memorizing the 6 rules. You have to figure, I don't know why they don't do that, but they go by the rules. Okay. That's what I wanted to cover today. This is the qualitative aspect. For your break, you're going to have a week off. So there's no school a week from today. No school a week from tomorrow. And it's weird. Back City's spring break was last week. So they're just finishing up. And Sac City and Sierra are never together. They're always a week or 2 apart. So my holidays are never together. Okay, any last minute questions about qualitative aspect? Now, when we get back from break, we're going to get into heavy duty math again. The quantitative aspect of solutions is moles per liter. Say again. Tomorrow? Look over the practice test. Basically, there's going to be conversions like grams to mole, grams to number of particles, balancing equation, some stoichiometry problems, 5 grams of water is produced in this combustion of methane, how much methane is used, and then there's the take-home problem, which is a limiting reactant problem. Okay, so if you look at practice test 4, and look at page 1, not page 2. Page 2 gets into double replacement reactions we haven't covered yet. And the reason why it's practice test 4 is because it used to be unit 4. And I have a lecture on that as well. On that 2 back, or went over the practice test. So review that. Okay, anything else? Okay, let me finish this off here.